Sure,
Right.
let's start. Yeah. So the next speaker will be Kevin Cahill, and he'll talk about local Lorentz invariance and dark matter. Please go ahead.
Hi. Well, good morning, people in Asia, and good evening, people elsewhere. I'm going to talk about, as the title suggests, gee, I'm not able to, I can't get the, let's see if this works. Ah, there. Okay, so I'm going to be talking about the fact that general relativity with fermions has two independent symmetries. One is general coordinate invariance. That's the traditional symmetry of general relativity, the well-known symmetry. And the second symmetry is not mentioned very often. I've never seen it actually, and it's local Lorentz invariance. And in traditional general relativity, local Lorentz invariance is implemented by something called the spin, oh God, I've forgotten now what it's called. The spin, I'm terrible with names. Let me just, anyway, what I'm suggesting here is that it may be implemented by bosons that have their own Yang-Mills-like action. I'm calling these L bosons, L for Lorentz. These L bosons would couple to fermions and generate a potential that violates the weak equivalence principle. Experiments have shown that L bosons, if they exist, are nearly stable and contribute to dark matter. So once again, general relativity with fermions has two independent symmetries, general coordinate invariance and local Lorentz invariance. So I'm confused as to, all right, anyway, in standard formulations, local Lorentz invariance is implemented by the spin connection. Here, this omega sub I. I'm suggesting that it may be implemented by gauge bosons that have their own Yang-Mills-like action. Such L bosons would couple to fermions and generate a potential that violates the weak equivalence principle. And if they are massive, the inverse square law as well. Experiments looking for such potentials imply that the bosons, if they exist, are nearly stable and contribute to dark matter. Now let's see if I can go to the next slide without screwing some things up. In standard formulations, the covariant derivative of a Dirac field looks like this, where this is the spin connection. These are ordinary gamma matrices. Here I'm using a 4-component Dirac spinner. The spin connection is involves the Levi-Civita connection gamma, and then Cartan's tetrads, derivatives of the tetrads and a quadratic expression in the tetrads. The Levi-Civita connection in turn is defined in terms of derivatives of the metric tensor and the inverse of the metric tensor. Whoops. And the metric is quadratic in Cartan's tetrad. So this is the standard formulation. And what bothers me about this formulation is that this coupling to fermions is just so, frankly, ugly. I mean, look at that thing. And since the metric is quadratic in the tetrads, the spin connection, the traditional spin connection is of 6th order in the tetrads, because we have here second order, so that's 4th order, 5th, 6th order. Now, in the standard model, we're accustomed to associating a gauge field with every symmetry. And the gauge field has its own action, a Yang-Mills action. If this pattern extends to gravity, then local Lorentz invariance would have its own gauge fields, 3 for local rotations and 3 for local boosts. I'm calling these L bosons L for Lorentz. L bosons gauge local Lorentz transformations. And here then the expression of the covariant derivative acting on a Dirac spinner is like in the standard model, namely it's some sort of matrix times a vector field. And these L bosons then define a field strength as the commutator of the covariant derivatives, and they have their own Yang-Mills action. That's what I'm suggesting. Now let's look at a general coordinate transformation and the way I distinguish between a general coordinate transformation and a local Lorentz transformation. The general coordinate transformation acts on coordinates and acts on world indices. Whoops, sorry. And so a gauge field, electromagnetic field, transforms this way under a general coordinate transformation. On the other hand, the Cartan's tetrads transform this way with no change on the Lorentz index. A Dirac field under a general coordinate transformation just changes by virtue of the change in its coordinate. And the L bosons that I'm suggesting may exist transform this way just because of their one world index. A local Lorentz transformation, on the other hand, acts on Dirac and Lorentz indices, but leaves world indices and coordinates unchanged. So the electromagnetic field is totally unchanged. The Cartan's tetrads transform according to a Lorentz transformation. A Dirac spinner transforms this way with no change in the coordinates. And the L bosons transform this way like a Yang-Mills boson. Just to check that the Dirac action is actually invariant on the local Lorentz transformations, we can just recall these standard formulas for how gamma matrices play with Lorentz matrices. And from that, it follows that whoops, what happened? That gamma contracted with the Cartan's tetrads is invariant. And so the Dirac action density itself just turns into this expression. And because this derivative is actually covariant, you just get a D inverse. And then this structure, this D inverse adjoint goes across via this relation. And then D inverse on the contracted gamma with the tetrad just leaves something invariant. So the Dirac action density is invariant under a local Lorentz transformation, no coordinate transformation. By the way, this is different in the case of flat space. In flat space without tetrads, there's a conspiracy between the how the Dirac matrices and the space-time transformation of a flat Lorentz transformation and flat fat Minkowski spacetime, how those things conspire to make the Dirac action invariant. Anyway, the matrix of Lorentz gauge, let's say L boson gauge fields looks like this. If you expand the Dirac matrices, it has a Hermitian part that looks like that. Now, what about these L bosons? They may be massless, and that's probably the most likely case. On the other hand, a Higgs mechanism is possible. And for example, the time component of a field that is a world scalar and a Lorentz vector, if it got a non-zero average value in the vacuum of our pocket universe, suppose it did, well, then the kinetic action of this field that I wrote as V, I guess V for vacuum, it would give masses to the three L bosons that gauge boosts. Now, if the L bosons are massless, then experiments show that their coupling to fermions is very weak. Now, in fact, no experiments have been done looking precisely for L bosons. Instead, what's been done is experiments looking for bosons of or departures from Newton's law of gravity or from Einstein's law of gravity. And the limits on these are very, very severe. And consequently, the L bosons, if they exist and are massless, they interact very weakly of order gravitational weakness. And so they were not in thermal equilibrium in the early universe unless our pocket universe was had reached Planck temperatures. So they don't affect the transition from the era of radiation to the era of matter. On the other hand, if the time component of this field D, that's a world scalar and a Lorentz vector, if it is non-zero, well, the change in the angular momentum generators looks like this, and it basically commutes with the parts of the fields of the standard model, so it wouldn't really show up any breaking of angular momentum. Now, massive L bosons coupled to fermions and make Yukawa potentials, and the standard way to, or a standard way to parameterize these is to, or at least the way I do it for the case of L bosons as opposed to general fifth force bosons, is with a parameter alpha, a scale lambda, and mass factors out in front. But this alpha has to do with how many fermions are in a given mass and also a coupling constant. Now, I'm going to review some of the experiments. The Riverside and Indiana and Purdue group have placed upper limits on the strength of Yukawa potentials that violate the inverse square laws at differences, at short distances between 1/100th of a micron and 100 microns. So those were quite remarkable experiments. The Washington group tested the inverse square law at slightly longer distances between a micron and a millimeter. A Chinese group, interestingly enough, at Wuhan, tested the inverse square law from 2 microns to 3 millimeters. And the Washington group tested the weak equivalence principle over longer distances from 1 centimeter to 10 to the 13 meters. And so you see these limits are that the strength is quite weak. Recent measurements by the microscope satellite mission have lowered the upper limit on the strength of Yukawa potentials that violate the weak equivalence principle by about an order of magnitude, again, between 1 centimeter and 10 to the 9th meters. So summarizing all that data, what we can say is that there's a region that's excluded, and the scale for these various scales in meters from 10 to the -9 to 10 to the 9th, that's 18 orders of magnitude. And here, 30 order of magnitudes of strength. This is basically what's allowed, the white region. And this region in here is a region in which massive L bosons would contribute something to dark matter, but not all of dark matter. On the other hand, if we're over here, the L bosons would contribute to more than the known amount of dark matter. So I think the summary is that L bosons were in massive L bosons were in thermal equilibrium at very early times. Experiments put upper limits on the strength of the potential between fermions for L bosons of a given mass. These L bosons therefore interact weakly and decay slowly, and therefore are still around. So the experimental upper limits, in a curious way, point toward dark matter, not away from it, because they say that if massive L bosons exist, they're still here. Experiments put lower limits on the masses of L bosons that interact with a given strength. And whether massless or massive, the L bosons contribute to dark matter if they exist. On the other hand, the contribution of massless L bosons would be very, very small. I'm afraid that this is a duplicate slide, effectively. Conversations with Rusba Alaverdi, Francis Yan Sirosine, Bobby Middleton, and Leanne Yenavu improved this talk. And here's the first page of that paper that describes all of this in much more detail. And on the left is an advertisement for the second edition of my book on mathematics. So I gather that I have ended early.